Chapter 12. Structure of Alloys and Steels. Let's suppose we have a hot liquid alloy containing two different metals. While the alloy is in liquid form, the atoms from metals A and B can mix and move around freely. As the liquid cools and forms a solid, the metals will try to form crystal structures. What type of crystal structures will they form? The type of alloy structures formed depends on the solid solubility of the component elements. Solid solubility means whether the alloying elements can dissolve in each other as solids. If the alloying elements can dissolve as solids, this means both elements fit in the same common crystal structure. At a larger magnification, the alloy only has grains of the same type, and both elements are dissolved in each crystal grain. If the component elements cannot dissolve as solids, this means the component atoms cannot mix, and instead form separate side-by-side metal crystal structures. The separate metal crystals grow in layers or stripes in what is called a lamellar structure. There are three main types of alloy structures. In a solid solution alloy, the component elements dissolve fully in each other as solids, and we get a single crystal structure with both A and B atoms in it. The alloy appears as grains of solid solution crystals. Copper-nickel is an example of a solid solution alloy. In a eutectic alloy, the component elements do not dissolve in any way as solids. We get alternate layers of the two different metals in a lamellar structure. This structure is also called a eutectic. Cadmium bismuth is an example of a eutectic alloy. In a partial solubility alloy, the component elements will only dissolve in each other at low concentrations or high temperatures, and thereafter won't dissolve anymore. This means we get a mixture of solid solution grains, where the elements have dissolved at low concentrations, and lamellar grains, where the elements cannot dissolve any further. Tin lead is an example of a partial solubility alloy. There are three ways that a solid solution crystal can be formed. In a substitutional solid solution, atoms from the alloying element take the place of metal atoms in the same crystal lattice. Copper-nickel is a substitutional solid solution alloy. In an interstitial solid solution, atoms from the alloying element fit in the spaces between the metal atoms in the lattice. Ferrite is an interstitial solid solution alloy. Small amounts of the small carbon atoms can fit in the spaces between the larger iron atoms. Solid solution alloys can also be a combination of substitutional and interstitial structures. In stainless steel, small carbon atoms fit in the spaces, while large chromium atoms take the place of iron atoms in the lattice. Alloys are stronger and less ductile than their constituent components. This is because the alloying process creates more tension in the crystal lattice, which makes it more difficult for atoms and dislocation defects to move. To understand the structures of steel, we must first understand the allotropes of iron. Allotropy means the same element can exist in different physical forms. In the same way that carbon can exist as graphite or diamond, iron can exist as ferrite or austenite. Iron exists as ferrite at room temperature and up to 910 degrees Celsius. Ferrite has a BCC crystal structure and can only dissolve up to 0.02% carbon. Between 910 and 1390 degrees, iron becomes austenite. Austenite is a solid with an FCC crystal structure and can dissolve up to 2% carbon. This difference in carbon solubility between austenite and ferrite causes different kinds of steel structures to be created, as we will see in the next slides. Steel is an alloy of iron and up to 2% carbon. When liquid steel is cooled, it first goes through an austenite solid solution phase. If there is less than 0.02% carbon in the austenite will cool directly to form grains of ferrite. All of these small amounts of carbon can be contained within the BCC ferrite solid solution. When austenite cools that contains more than 0.02% carbon, but less than 0.8% carbon, ferrite is created as before, but the ferrite can only contain up to 0.02% carbon, so the excess carbon must come out of solution. The excess carbon atoms chemically combine with iron atoms to form iron carbide. Iron carbide is a very hard substance, which is also called cementite. Because we now have a partial solution alloy, we get a eutectic structure composed of alternate layers of ferrite and cementite. This eutectic structure in steel is called pearlite because of its shiny appearance. What happens in the final steel microstructure is we get a combination of grains of pure ferrite and grains of perlite. The more carbon in the steel, the more perlite grains are formed. Perlite makes the steel stronger and harder because of the hardness of the cementite. If we slowly cool austenite that contains more than 0.8% carbon, we get all grains of perlite and no more ferrite grains. However, perlite cannot hold more than 0.8% carbon, so the excess carbon that comes out of the austenite gets converted to even more cementite, which gets deposited on the boundaries between the perlite grains. This additional cementite starts to make the steel a lot harder and more brittle, which is what we get in high carbon steels. One way of creating very hard steel is to cool austenite with medium to high levels of carbon very quickly. What happens here is that the excess carbon does not have time to come out of the austenite, and a distorted needle-like structure called martensite is created. Martensite is a very hard and brittle material. We will see more of martensite later in Chapter 14, Heat Treatment. Here is a summary of the main steel structures and how they are created. Summary. A solid solution alloy means the alloying components fully dissolve in each other as solids. The alloying components fit in the same crystal lattice. In a substitutional solid solution alloy, the atoms of the alloying element take the place of metal atoms in the lattice. In an interstitial solid solution alloy, the atoms of the alloying element fit in the spaces between the metal atoms in the lattice. In a eutectic alloy, the alloying components do not dissolve in each other as solids. A laminar structure is created consisting of thin layers of the two different metals. In a partial solubility alloy, the alloying components only partially dissolve in each other, and so we get a combination of solid solution and eutectic structures. Steels are an alloy of iron and up to 2% carbon. Austenite is an allotrope of iron that exists at high temperatures only. It can dissolve up to 2% carbon. Ferrite is an allotrope of iron that exists at lower temperatures. It can only dissolve up to 0.02% carbon. It is soft and ductile. Cementite is also called iron carbide and is a hard and brittle substance. It is created when austenite cools to form ferrite and the excess carbon must come out of solution. Perlite is a lamellar structure of alternate layers of ferrite and cementite. Martensite is formed when austenite containing sufficient carbon is cooled very quickly. It is a very hard and brittle needle-like structure.